Right, ladies and gentlemen, let's continue with chapter 4 on transient heat conduction. We've already completed the first part, which was on the lump system analysis. The lump system analysis is typical valid when the Biot number is smaller than 0.1. In the calculation of the Biot number, there's a characteristic length, which we determine by taking the volume divided by the surface area. In general, remember that is just for the lump system analysis. The Biot number is smaller than 0.1. In general, then we can use the lump system approach. The disadvantage of the advantage of the lump system approach is it's so simple and very easy to do a calculation. The disadvantage is you cannot get the temperatures at different positions inside the body. So you cannot, for example, determine the temperature on the surface and in the center, or the temperature 2 or 3 millimeters from the surface. You cannot do that. The temperature that you get is the temperature everywhere. Then we've made it a little bit more sophisticated. Paragraph 4.2, in which we have looked at the transient heat conduction in large plane walls, long cylinders and spheres with spatial effects. And with the previous lecture, I've just started with transient heat conduction in semi-infinite solids. SIS, as I've written here, is semi-infinite solid. So in terms of semi-infinite solid, that's a body that's very large in terms of all the dimensions, but it has one specific surface, which is a flat surface, and where the temperature of this body is Ti, at T equal 0, this temperature would be equal to Ts. Okay. And we are interested in getting the solution for this problem. The practical examples are, for example, cases where we want to look at the surface of the earth, maybe a water pipeline, if it is going to freeze. That is one practical application. And other practical applications are almost any big body or relatively big body where we want to know how the temperature changes very close to the surface. That would also be valid to use the semi-infinite solid approach. Now, if we just look at the PowerPoints, and you will find these equations in your textbook. Oh, goodness. There you go. Okay. So we start with a differential equation. There it is given. And the boundary conditions and initial conditions. But what is different now in this approach is the definition of an eta. So eta is a similarity variable, and that is equal to x divided by 4 times the square root of 4 times alpha t. And the reason we use that eta is the result is going to be a normal differential equation, which looks like this. Okay, equation 1. And by using the boundary conditions, boundary condition 1, a boundary condition 2, as well as an initial condition, we can try to solve that equation. In that equation, we also make use of a so-called W. It is just to make the integration easier, as well as a so-called dummy variable, and the result is, you can go and look at the full derivation in your textbook. We make use of the separation of variable method to solve it, and the result is an equation which looks like this. T minus Ts divided by Ti minus Ts is 2 times divided by the square root of the integration from 0 to eta, e to the minus u squared du. where U is just a dummy integration variable. Now, this is equal to what is called the error function. The error function in eta. And the error function, it is something like the cosine function or the sinus function. And that can also be written as 1 minus the error function, take note, C, which means the complementary error function, that. And that is equation 443 in your textbook. Now, there's no analytical solution for this equation, and it has to be solved numerically, and the result of that is given in table 4.4. Okay, let me show table 4.4 typically to you. There it is, if you can just take a look at that. And if you look in the table, you will see typically different values of eta is given the solution for, and take note, the complementary error function, not the error function, but the complementary error function. And typically, if eta is equal to 0, then the complementary error function would be exactly equal to 1. And it would, let's look at typically 0.5. If it is 0.5, it is 0.4795. Typically for 1, it is equal to 0.1573. But something that should be noted, which is very good to notice, is that when eta is starting to become 3.6 and larger, this value would be approximately 0. And this thing, you will see later on, is a very useful result and it really can help us a lot if we do some calculations. Okay. So in general, there are 4 different types of solutions which can be generated by using different boundary conditions. So this is the boundary condition, the solution, where at T equals 0, the temperature on the surface changes to Ts. But the 4 cases which are given in your textbook, if I can show them schematically, is firstly, if that is the semi-infinite solid, and that is equal to X, then that temperature is equal to Ts, while this body, this semi-infinite solid that I'm showing here, is equal to Ti. So that is the case 1 type of solution. The case 2 type of solution, again the semi-infinite solid, and I'm just showing it schematically. There it is. At T equal to 0, there will be a heat flux on it, and the heat flux is constant. That would be, for example, a heater or solar radiation on a certain surface at T equals 0. And the heat flux stays constant. The third type of case would be the case, again there is X, where over this flat surface there's a temperature T infinite with a certain heat transfer coefficient. So a forced convection type of boundary condition. And the 4th type of boundary condition in your textbook if that is X, would be the case where we take a laser with a certain energy pulse, which can be described with the units a certain number of joules per square meter. And for all 4 of these cases, there are analytical solutions, and all of them can be written in one or other format in terms of the error function or the complementary error function. So the 4 cases are given in your textbook, and they've got different solutions. So if you look at these 4 different types of solutions, then it shows the temperature distribution for every one of them. And for the first case, it also gives the heat flux. And you'll see that some of these equations are quite long. Okay. You follow? Okay, let's do an example to make this clear. And the example that we're going to do, so if we look, let's suppose we call that case 1, case 2, case 3, and case 4. I'm going to do 2 examples today, and that is, I'm going to do an example for case 1 and an example for case 3. So let's look at case 1. A specified surface temperature. So for a specified surface temperature, the temperature at any point x minus Ti divided by Ts minus Ti is equal to the complementary error function of x divided by 2 times alpha t. And the problem that we're going to consider is the Earth, and on it we've got snow. Here's the snow. And the snow is going to be there for 3 months. And the temperature is going to be minus 30 degrees Celsius. So the surface temperature underneath the snow is minus 30 degrees Celsius. So this is typically in Siberia, not in South Africa. And there's a water pipeline under the surface. Okay. And the thermal conductivity is 0.4 watts per square meter Kelvin, that of the ground. And alpha is equal to 0.15 multiplied by 10 to the minus 6 square meters per second. And this is the water. And the initial temperature of the Earth is 15 degrees Celsius. Okay, so let's look at the problem. We've got the Earth originally at 15 degrees Celsius, then we've got snow, and the snow will be for a period of 3 months. We've got the thermal conductivities of the Earth, we've got a water pipeline, and the question is, how deep must this water pipeline be to ensure, let's rather call it an H, how deep must it be to ensure that the water doesn't freeze? Or the temperature is equal to 0. How deep must it be? Okay, so how deep must this be for this temperature to be 0 degrees C after 3 months? So this is the equation. So in terms of all 4 different cases, which is possible, this is the easiest case. So in terms of this solution, if we look at this, we want to know when will the temperature be 0 degrees, so it's 0, minus 15, divided by the surface temperature is minus 30 minus 15. Okay. And that is equal to 0.333, which is also equal to the error function, the complementary error function of x divided by 2 times the square root of alpha t. So if we go and look at table 4.4, it means that we want to know at what error function, at what complementary error function for x divided by 2 times the square root alpha t would that be equal to 0.333? And if you go and look in table 4.4, for those of you who've got your textbooks here, okay, so take note, that is not for eta 0.33, it is for the complementary error function must be 0.33. And if you look at that, you will see it is where eta is equal to 0.6841. If you go and do a little bit of linear interpolation, and that is equal to x divided by the square root of 4 times alpha t. I can put the 4 inside, or I can put the 2 outside this, just how you want to do it. So 0.6841 is equal to x divided by the square root of 4 times alpha. It's been given as 0.15 multiplied by 10 to the minus 6 multiplied by t. What is t? T is equal to the number of months. It's 3 months, approximately 30 days in a month, multiplied by the days, 24 hours, multiplied by 60 minutes, multiplied by 60 seconds. So that is just the time in seconds, and that is equal to 7.776 multiplied by 10 to the 6 seconds. Approximately 7.8 million seconds, 3 months. So 7.776 multiplied by 10 to the 6. And if we then go and calculate x, which is now equal to this height, it would be equal to 1.478 meters. So the water pipeline must be deeper than 1.5 meters to ensure that the temperature in it doesn't drop to lower than 0 degrees Celsius. Okay? Yep, question.
First of all, the eta there is x over 4 square root 4 alpha t, is that right?
Yes, it doesn't look right. I can't remember. You can just check there for me. So it's either this 4 or that 4. Okay. With the previous lecture, I told you there's a difference between what I mean and write sometimes. But I think it's worse than that. There's a difference between what I mean, what I say and what I write. Okay. So you can just check in terms of how it should be. Okay, do you follow that, this first case? Okay, now let's do the third case. Case 3. Okay, now when students get this type of problem in the test or exam, they think that I must have been in a bad mood to ask you this problem. Because if you look at the solution of the third case, there you will see that it is quite a long equation that you need to calculate. Do you get it? Okay. So this third case, it is something similar than the previous problem. Here we've got now winds, the temperature of minus 10 degrees Celsius, with a heat transfer coefficient of 40 watts per square meter degrees Celsius, and it is going to blow for a total of 10 hours. We've got the soil or the earth, which is originally at a temperature of 10 degrees Celsius. The thermal conductivity is equal to 0.9 watts per meter Kelvin, and alpha is equal to 1.6 multiplied by 10 to the minus 5 square meters per second. Alpha, the thermal diffusivity. Okay, now the question is determine the temperature at x equal 100, 200 and 500 millimeters from the surface. Determine the temperature at x equal 100 millimeters, 200 millimeters and 500 millimeters from the surface. And let me see if I can write this equation correctly. Txt minus Ti divided by T infinite minus Ti is equal to the complementary error function of x times the square root of 4 times alpha t minus the exponent of hx k plus h square alpha t k square, everything multiplied by the complementary error function of x times divided by the square root of 4 times alpha t plus the heat transfer coefficient multiplied by alpha t divided by the thermal conductivity K. There's the equation, a long equation. Okay. Now the best advice I can give you is to go and calculate these terms first before the substitution. So let's look firstly at x divided by the square root of 4 times alpha t. Okay. So we are first going to look at a depth of 100 millimeters from the surface, 0.1. divided by the square root of 4 times 1.6 multiplied by 10 to the minus 5, and the time is 10 hours multiplied by 3,600 seconds. That is 36,000 seconds, 10 hours, and this term would be equal to 0.066, something like that. Okay, the next one is hx divided by k. The heat transfer coefficient is equal to 40. The depth is 100 millimeters. The value of k is 0.9, and that is equal to 4.441. Am I going too fast? Are you keeping up with me? Okay, the next term, the heat transfer coefficient multiplied by alpha t divided by k is equal to the heat transfer coefficient is 40 squared multiplied by alpha, 1.6 multiplied by 10 to the minus 5, The time, 10 hours multiplied by 3,600 divided by 0.9. I think it should be 0.9 square, so there should be a square there. And that is equal to 1138. And then lastly, the term heat transfer coefficient multiplied by alpha T divided by K is equal to 40 multiplied by the square root of 1.6 multiplied by 10 to the minus 5. 10 hours of 3,600 seconds divided by 0.9 is equal to 33.7. Right. Are you all happy with that? Is there anybody that can see an easy way out of these calculations? Any easy way out? Okay, so I've done it, one term at a time. However, if you've done quite a number of these calculations, the best advice I can give you is first to start there. Because if you do that, what can you notice? I want to come back to table 4.4. I've said this is a very important thing to notice. So if eta is larger than 3.6, then the complementary error function would be 0. Okay? So if we use that and we look at this term, this part is equal to 33.7. You see? This one, x times is 0.066, but in any case it's a plus. Okay. So if you look at this, you can see that this term is equal to 0. Okay? If that is equal to 0, then you multiply this by 0, so it means that all that disappears. And you end up with a very simple equation which gives the temperature Txt minus Ti as T infinite minus Ti is equal to the complementary error function of x divided by the square root of 4 times alpha T. It's really much easier than just putting in everything in the equation and go through all the calculations. Okay. So we want to determine the temperature at a depth of 100 millimeters. So we want to determine the temperature. Let's put in there 100 to indicate it is 100 millimeters from the top minus the initial temperature of the Earth, in this case was 10. Divided by T infinite is the temperature of the cold wind, which is minus 10 degrees, minus 10, and that is equal to 0.92. Where do I get the 0.92? Because if we go and calculate the complementary error function of 0.066, remember, is this value here. From it, we get the value of 0.92, so that is from table 4.4. We substitute it in there. The only unknown is the temperature at 100 millimeters from the surface, And if you calculate that, it is going to be minus 8.4 degrees Celsius. Okay. Now you can go and also do the calculations for 200 millimeters and for 500 millimeters. And I've calculated minus 0 degrees Celsius and minus 2.8 degrees Celsius. Any questions, ladies and gentlemen? If not, then thank you very much. That is then the end of paragraph 4.3. And with the next lecture, we will do the last part, which is more the three-dimensional cases. Thank you very much.